Hello, this is Professor Todd Elliott, and in this short tutorial, I will demonstrate how to measure the firing angle on an SCR control circuit. Okay, so here's our circuit, and on the right-hand side here, we have our nominal 12-volt transformer. We have the SCR. This is the anode. This is the gate. Or sorry, this is the cathode, this is the gate. R4 is RL, this is we're using as the load resistor. Diode D1, it's there. Notice the orientation, cathode to anode. This is an IN4001 or similar power diode. Its purpose is to prevent large negative voltages from reaching the gate, which on this SCR has a maximum rated voltage of about -6 volts. So we need to protect the gate circuit from those negative voltages. And of course, on this side, only the positive half AC cycle will be permitted. Over here we have the UJT 100 ohm resistor in both the base 2, base 1 terminals. This is the emitter. Just a little note that the base terminals are not interchangeable. Okay, so they must be wired exactly how it's shown. Over here we have a fixed 470 ohm resistor. This is a 104 potentiometer, which is 100K. And by putting this jumper here from the wiper to the outside, then we're turning this into a rheostat, so we have variable resistance. So in essence, the setting of P1 in conjunction with the fixed resistor here and the capacitor determines the RC time constant, which determines how long it takes for the emitter voltage on the UJT to build up sufficiently and then turn on, and that's called the peak point voltage. And then it will basically turn on suddenly. The UJT switches into conduction with the sudden current pulse appearing through R3 here. By Ohm's law, it generates a voltage pulse, which we'll look at on the scope shortly. And that's what's used to fire the gate. Okay, and by controlling the resistance here, you can control the how long it takes for the capacitor to charge, and therefore how long it takes for the UJT to fire. So if you were to set P1 to the zero resistance position, we would just have R1 and C1, the 100 nanofarad capacitor. That would be a minimum charging time constant. It would cause the voltage across the capacitor to build up more quickly. The UJT would fire earlier in the cycle, and therefore the SCR would be conducting earlier in the cycle, and therefore deliver more average power to the load. So remember that the SCR works, just think of it as a switch, and as you fire it earlier in the circuit, then it will then essentially the switch will be closed for a longer time period, and current will flow through the load for more of the cycle, and therefore higher average power. As we increase the resistance of P1, then we will slow down the time it takes to charge the capacitor. The emitter voltage on the UJT will take longer to reach that critical peak point voltage, and therefore it waits a little bit longer later in the cycle to build up sufficiently to trigger the UJT to generate the gate pulse to trigger the SCR. Therefore, the average load power will be reduced because the switch, the SCR, is not closed conducting for as long as period of time. Okay, I'm going to switch over to my oscilloscope here. Okay. All right, so basically what I have here on the yellow trace I'm using as on my toolbar there as channel 1. You can use whatever channel you want. That's currently connected to the anode of the diode. So channel 1 is measuring just the straight up AC voltage. Channel 4, the green one, so if I have a 4-channel scope, is connected up to the anode. So it's measuring the anode to cathode voltage. And if you just noticed, as I adjust P1, okay, don't worry about those little spiky things there. That's a little bit of filtering would take care of those. It is just built on a breadboard. See if I turn that down, see the minimum position here, that little green peak there. Okay, that's the sort of the minimum firing angle, right? So notice how the zero crossings are aligned. I've used my horizontal control to align the start of the positive half cycle right on the center line of the scope. You can put it wherever you want, but with that adjusted to the minimum firing angle, therefore you notice that doesn't go quite to zero, and the reason is you can't trigger the SCR at 0 degrees because it needs a little bit of current to switch it into conduction. Okay, so as we turn it up over to here, and I've just put a line here. These are my cursor lines, the two dotted lines there. So that's about the we'll take some measurements. That's about the 90-degree point, right? And it continue on and on and on and on and on. And notice how then, right? And there is a vertical line here. You can just see it, right? That's as far as you can adjust it, because once you get to this point, you can't go any further because it'll drop below the holding current and the SCR will switch off. Okay, so basically, let's just kind of set this in the center here. Now, there's different ways to measure the phase angle, which is the firing angle, which is just how, see here, this bit here, how long it takes, it waits in the cycle to fire. It's just phase displacement. You can use the, if your scope supports it, use the auto phase measurement. You can manually count divisions, or you can use the cursors. I'm using the cursors because it's a fancy scope and it has them. And I think it's kind of an easy way to do it. Anyway, so you know what that one AC cycle is 16.6 milliseconds, but the SCR can only conduct during half the cycle. Okay, so therefore half the cycle would be half that, so 16.66 divided by 2, and that would be 8.33 milliseconds is the duration of the half cycle. Okay, so if you were to use the place the cursors here, and I've just, okay, so let me just adjust it just to line up where I have the cursor line now, okay, which is about the 90-degree point. Measure this time duration, okay, and you can see here it's 4.44, so that's like your little t. So if you take the 4.44 divided by big T, or the half cycle period, which is 8.33, divided by 8.33, and then times 360 degrees, then by what do I say, 4.44 divided by 8.33 times 180, because we're only working in half a cycle, not 360, sorry. Okay, that's calculates 95.94, which I eyeballed about 90 degrees. Okay, and you can see that's pretty close. So let's turn it all the way here. Okay, so I'm increasing the resistance of P1, so I'm making it the SCR wait longer in the cycle. It takes more time for the capacitor to build up a charge to fire the UJT. I'm going to push it all the way. That's as far as my adjustment goes. And then I'm just going to go to my cursor feature here. Okay, I'm just going to slide that line over to there. Okay, right. And now we're going to measure the different. I'm just leaving this one on the 0 here, on the 0 crossing. It's going to measure then between the dotted cursor lines the time duration. Now it's 7.08. Okay, so you take the 7.08 divided by the half cycle period, 8.33, times 180 degrees. that gives us 152, say 153 degrees. And that looks about right, because we know if you could fire over the whole half cycle, which you can't, it'd be 180 degrees. So it's 153, so we're a little bit less than that. Just FYI, this little bit here, that's called the conduction angle. So that's the duration during which the SCR is in conduction. Okay, so if we were to take the 180 degrees minus the 153, okay, that would mean our SCR conduction angle is 27 degrees. Okay, so the conduction angle is for how many degrees is the switch closed? Does the SCR conduct? Does load flow through the current? Or current flow through the load, sorry, right? The firing angle is how long does it wait to turn on? So, but those two angles always add to 180 degrees. So let me go and spin this down back the other way. We're going to fire it earlier in the cycle, so we're going to set it to the minimum resistance position. And I'm just going to slide this all the way back to here. Okay, over to there. Okay, so now we have 0.48 milliseconds. So now I'm going to take the 0.48 divided by the 8.33 for the half cycle times my 180 degrees, and that's 10.4 degrees. So you can see that's just at the start of the cycle. And in that case then, right, the big area in the center here, that's going to be the conduction angle. So if you take 180 degrees minus that, 180 minus that, it's 169.62 degrees. The conduction angles, and this time we're firing it as early in the circuit as possible, so the SCR is conducting as long as possible. If you were to go and put your meter across the load, you would find that's the highest average load voltage. And then as we increase the firing angle, excuse me, then the SCR is conducting for a shorter period of time, and the average load voltage goes down. Okay. Now, please don't put the oscilloscope across the load, because you'll force a second ground in the system. It won't like that, so don't do that. But you can measure it with your meter. And I'm just going to momentarily just connect channel 3. Hey, it is a 4-channel scope, so why not use it? Okay, that there I have connected on the gate pulse and feeding into the SCR. That's the purple and magenta line. Okay, and you see there then, right, how there's a vertical line there. So this is when the UJT switches into conduction. So this is the gate pulse going into from the UJT into the SCR, and then no, surprisingly, that aligns exactly with the firing angle. So you can see very nicely the three waveforms there, and how they all match up. So anyway, I hope this was useful and to help you measuring angles on the firing angle for the SCR. Right, thanks, cheers, many blessings, have a good day.